Hello. Today we're going to be talking about systems of linear differential equations and how to solve them. So a system of linear differential equations takes the form of dx dt is equal to matrix A times an x vector, or in other words, our solution function. If you've taken linear algebra, you know that this looks eerily similar to an eigenvalue times an eigenvector. If you haven't taken linear algebra, it's important to note how important eigenvalues and eigenvectors actually are. So real quick, we want to talk about an eigenvector and eigenvalue. Eigenvectors are essentially a scalar value where if you multiply it times an eigenvector, all that's happening to the eigenvector is a transformation, a scalar transformation essentially. So in other words, let's say you have two vectors like this, and they both have some direction A. Or sorry, they both have some magnitude A with the direction, I'll call this one J hat, and this one will be A times I hat. Oh, maybe I should use a different value for that actually. I'll call it B. We'll call it, each one as B. What the scalar value does is it basically multiplies a scalar to these vectors, essentially elongating them or shortening them. This scalar gives you the same essential stretch as multiplying A times the eigenvector. So why is this important for differential equations? Well, it's important because if we have a system like this, where dx dt is equal to A times x, you can essentially rewrite this as ax is equal to the eigenvalue times the eigenvector. How do you use eigenvalues and eigenvectors essentially? Well, the simple approach is to basically find the eigenvalues. And to do that, we take this approach. We're going to move this side over to the left. And by doing that, we can now multiply both sides times the identity matrix. And so the identity matrix times A is just A, but the eigenvalue times the identity matrix is lambda times I. We could also take out this x. Now we have something that we can more easily solve. So essentially, to find the eigenvalues, you would take the determinant of this matrix. And so the equation we're going to be using is this. Okay. Now, how does this help us in the long run? Well, if we remember back to our differential equations, we typically take the form of, let's just call it a regular solution y is equal to some constant times e to the rt. This would be for like a first order or second order. What we can do here is we can say, well, let's let x be equal to some vector, which will be the eigenvector, and I'll call this It's a bad symbol. I'll call this mu. Mu times e to the lambda t. And remember, we can add as many eigenvalues as we get. So for a system of linear differential equations in a 2 by 2 where your matrix is a 2 by 2, so A is a 2 by 2 matrix, you should end up with two eigenvalues or one distinct one. Either way, you'd end up adding some other solution with a different eigenvalue. Eigenvector, my bad. And eigenvalue. Okay, so let's do an example. We're going to say that we have a dx dt is equal to 3, 6, -1, -2 times x. Okay, so the first thing we want to do is we want to find our eigenvalues. And we go about by doing the formula we used before, which is a minus lambda I. And we're going to find the determinant of this. Set that equal to 0 so we can find our eigenvalues. Okay, so in this case, we're going to have our determinant. Let me write this out like determinant of A is going to be, oh, it's the determinant of A minus this. So we're going to have A, which is 3, 6, -1, -2, minus this matrix, which if you remember, the identity matrix is 1, 0, 0, 1 for 2 by 2. So then multiplying the scalar by it, you would end up with lambda 0, 0. So then we're just going to subtract minus lambda here and minus lambda here. Let me give myself more room. Okay, now we want to find the determinant and set this equal to 0. So to find the determinant, we're going to use our rule AB AD minus BC. So we're going to go here, and then we're going to go backwards. So this is for a general matrix where our matrix is A, B, C, D. So this is the rule we're using. And so when we do that, we're going to end up with, oops, 3 minus lambda times -2 minus lambda minus 6 times -1 is equal to 0. And so when we simplify this, we're going to end up foiling. So we're going to have -6 here, and then we're going to have +2 here, and then we're going to have a lambda squared here, and then we're going to have a -3. This is a 6 lambda. And then over here, we're going to have plus 6 equals 0. Okay. So our 6's cancel out, and we're left with lambda minus lambda. Lambda squared minus lambda. If you factor this out, you would see that we get lambda times lambda minus 1 equal to 0. So now we can solve directly for our eigenvalues, and we end up getting 0 and 1. Okay, now we need to find our eigenvectors. To find our eigenvectors, we'll use the same equation we used before, except we're not going to take the determinant. Instead, try to visualize it as if you're doing a minus lambda I times an eigenvector. So I'll call this mu actually, is equal to 0. So we would end up getting, in this case, our matrix is 3, 6, negative 1, negative 2. So we're going to do a similar thing. We're going to have 3 minus lambda, 6, negative 1, negative 2 minus lambda. We're going to get this times mu is equal to 0. If you know anything about matrices, you know that you can augment a matrix. Before we do that, let's actually plug in what our eigenvalues are. So I'll do eigenvalue is equal to 0 for our initial eigenvector. And we'll call this eigenvector 1. So when we do this, we're going to end up with 3, 6, negative 1, negative 2 times mu 1 is equal to 0. Okay. From here, you can see that the top and the bottom are very closely related. I'm going to do simple row. I'm going to first augment the matrix. So we end up with 3, 6, negative 1, negative 2, 0, 0. And then you realize that if you did R1 turns into R1 over 3, you'd end up with, this is a very bad 3, my bad. 3, you'd end up with 1, 2, negative 1, negative 2, 0. So we can recognize that these two rows are the same. So essentially, if we add them together, if we did R1 turns into, or rather R2 turns into R1 plus R2, you can see that this would just turn into 0. And so now we have a row of zeros. Anytime you're solving for eigenvectors, you should always get a row of zeros. At least in systems of linear differential equations. That's not always the case in linear algebra, but in this a typical process, you should always end up with some parameterization. Okay, so now what we're going to do is we're basically going to say, we're going to go back here, I'm going to say mu1 is equal to mu11 and mu22. Or mu12, sorry. You don't have to do this, I'm doing this for notation's sake, but anyway. So I'm going to go ahead and erase this. And we'll be left with this matrix here. Okay. So if you remember, we were multiplying everything by that. This is what we started with. So if we work backwards, we're going to know that multiplying this out, we should end up with mu11 plus 2 mu2 1 2 is equal to 0. Then we can say that mu1 is equal to negative 2 mu2. By doing this, now we have an equation for mu1 in terms of mu2. So let's say we let our mu2 or mu12 equal to 1. Now we know that our mu1 will be equal to negative 2, and then our mu2 is equal to 1. So then our eigenvector, our first eigenvector, turns into negative 2, 1, 2. Sorry, negative 2, 1. And this is our first eigenvector. I'm going to go ahead and erase most of this. That's the general process. And so for the next time, we're going to basically use, we did 1, or sorry, we did 0, so now we're going to do 1. So we're going to do a very similar process. I'm going to go ahead and move this up here. Back to it later. We'll come back to it in our final solution. So again, we know that our matrix A is 3 minus lambda, 6, negative 1, negative 2, minus lambda. We're going to augment this with 0. We now are going to do lambda is equal to 1. So then we end up getting 2, 6, negative 1, negative 3. Augment this. Again, what you'll notice is the top and the bottom rows are very closely related. If you do two row operations, if you do R1 turns into R1 over 2, this ends up turning into 1 and 3. And then if you just add R2 to R1, the bottom row turns into 0. And so we can do a very similar process, except this time we'll say this is our second eigenvector. And we're going to basically do, we'll call this 2, 1 plus 2, 2, 3, 2, 2 is equal to 0. Then we can solve again. And we will say that mu2, 2 is equal to 1. So then our new eigenvector is going to be negative 3, 1. So now that we have our two eigenvectors, we can write a general solution for our system of differential equations. So if you remember before, we made the statement that x is equal to mu times e to the lambda t. But we have 2, so we need to add them. So we're going to say that our solution is going to be, let me write this a little cleaner. Our solution is going to be mu1 times e to the lambda 1 t plus mu2 e to the lambda 2 t. And remember, this is our lambda 1, which we'll say is 0, and this was when we did lambda 2, which is equal to 1. Okay, so then we just plug everything in, and we're going to say that for this we have negative 2, 1 times e to the 0 t plus mu2, which is negative 3, 1 e to the 1 t. And then if we can simplify this further, you end up getting negative 3, 1 e to the t plus, this just goes to 1, negative 2, 1 as our final solution. And so there's a couple of things to remember Eigenvectors are basically vectors that fall within the space of the eigenbasis. So if your answer looks different than mine, that doesn't mean it's wrong necessarily. It just depends on what you chose your mu to equal when you ever solve for these, because eigenvectors are technically they form a basis. So this is just a general solution. I forgot to mention you should put your constants here. There should be two constants because you have two solutions. So this will be C2, add C2, and this is C1, and we'll write it as this. But you get two constants, and that's also why it truly doesn't matter unless you have an IVP. But if you don't have an IVP, I think it's okay to get different answers than this. I think most people typically just like to use the basis for the eigenspace as their eigenvectors, but technically eigenvectors could fall into, as long as they're in the eigenbasis, I don't think it's wrong to have it. Although I wouldn't take my word on it, but I don't think it would be wrong if you had like, I don't know, like -6 and 2 here. Because then that just means like your constant would be different. Right. So just keep that in mind. As long as it's like relatively equivalent, I truly don't think you have to get this exact answer, but it should look like fairly similar to this, and you should end up having two constants, and then sometimes you should get two e to the t's. In this case, we didn't because we had a 0, so that just went away. But yeah, just some things to remember. Your answer isn't automatically wrong if you did not get these. If you got something equivalent, I think that would also be okay. Anyway, thank you for watching. I hope this helped.